down, and therefore there's non-zero work being performed. Whereas on the yo-yo, it's true that at different moments in time, the yo-yo is moving down, right? So it seems like the same thing. But because it's rolling without slipping, if you like, on the string, because the part of the yo-yo that's touching the string is itself not moving instantaneously, albeit, there's no work being performed at that point of the yo-yo. It's a tricky thing. But there are two things. Yeah, when you use parallaxis theorem whenever you choose to use a pivot point that's different than the pivot point that was used to calculate the moment of inertia you're given. So suppose you've already got moment of inertia, or suppose it's easy to calculate from some, like the center of mass, or you're given the one from the center of mass. It doesn't be center of mass though. You could be given the moment of inertia on the end of a rod, for example, which is what, a third m r squared, or L squared, right? For L's length of rod. But you decide to use a pivot point that's somewhere else. Use it maybe, just some distance from the edge. If you want to use the parallaxis theorem, then what would you do? Parallaxis theorem relates the moment of inertia from the center of mass to some other place that's separated by distance d, right, with this formula. So if you have that problem, right, that's sort of interesting. So suppose you're given, so you have to use parallaxis theorem twice in that case. You'd say, well, I know the moment of inertia about pivot point 1, but I want to know it about pivot point 2. And parallaxis theorem relates each of those moments of inertia to the one about the center of mass. You see that? Suppose you're given that one, you want that one. Well, first what you do is you figure out what the center of mass moment of inertia is from that point, and then you go back and calculate this one from the center of mass. That's how I would do it. And the distances I'd use, d in that equation, would be initially that distance or that distance. So you might think, oh, I'll just stick in d from here to here, but I don't think that works. Stick that in. Because that distance squared doesn't equal that distance squared plus that distance squared. That's the thing about nonlinear functions, right? You gotta be careful. You can't just, they don't always add up, right? So, but this is a little, it could happen, I could ask such a thing. But all I'm getting at is when you use parallaxis theorem, you use it when you've got a formula for the moment of inertia that's about a certain point that's not the pivot point that you want to use. So you have to use parallaxis theorem relates specifically to the moment of inertia about the center of mass. You can't get these backwards. A couple lectures ago I got these backwards. I said it right and I wrote it wrong. Remember that? And so it's like I had a minus sign right here. But you always keep your head straight because you know the center of mass moment of inertia is always the smallest possible or the biggest possible moment of inertia. Smallest. So you better add a positive number to that in order to get the other one, right? Yeah. Center of mass is moving, but well, wait a minute. Did we say that okay. So that's a good question. So if we go back here, there's no let's get rid of all the extra things I stuck on. There's no bug. There's no rope. Just a rope going that way and force friction. Your question is, wait a minute. If no work is being done there or there, then how can it be accelerating? Well, no work is being done there because this part of the object isn't moving. Is this part of the object moving? It's rolling without slipping down here. I'm pulling the rope. When I did that, did the thing move? Which way is this part of the object moving? Momentarily. It's kind of weird. Huh? It's hard to think about. It's not to the left. So I don't have the demo here to show you. But if I pull this way right here, it's pivoting about this point. This is the stationary point in this object. And if I rock it back and forth, right, it's actually moving that way. You're doing positive work by pulling this rope on this spool. Does everyone see that? I pull the rope. It's rocking about that point. That point's not moving. No work being done by the friction or normal force. But work is being done. Is it positive work or negative work on the spool? If I pull that rope, starts off, it's holding still. I start pulling the rope. It starts to accelerate. Does it speed up? It went from 0 to non-zero. It sped up. Kinetic energy went up by conservation of energy. Like, I must be doing what? Positive or negative work on the spool. Positive work. And that's true because the force is that way from tension, and the spool, that part of the spool is moving that way. As upsetting as that may seem, or whatever, right? In fact, if you look at every part of the wheel, every single part of the wheel has a non-zero horizontal component of velocity, except right there. Is that true? Am I telling you the truth? I think I am. And I think they all are that way. They have different magnitudes. In fact, the velocity up here is bigger than the velocity down here. Think of it as a wheel rotating about this point. Right? That's what's happening. It's momentarily, that's what's happening. This thing is pivoting about that point right there. And so things that are further away from this point, right, have bigger velocity. And it's going clockwise. So the velocities are going like this. This problem, if you really think through and understand it, it's a lifetime thinking about that spool. All right, but anyway, all right, so people have hands up, yeah. Yeah, okay, yeah, so you're saying in this problem, so if you make a free body diagram of this wheel, and this wheel's got mass, let's say, this isn't just an ideal pulley, in which case this guy wouldn't care, he'd just fall under gravity, right? But let's say he actually has mass. So what are the forces acting on this wheel? Gravity? What else? Tension? What else? There's some nail through here, that's what you're asking about. So there's got to be some force from that nail acting on the wheel. Yeah, you can think of it as a normal force, or a nail force, you can call it whatever you want, but it's essentially a normal force. If there's no friction here, so let's assume there's no friction, meaning it doesn't, it's not like having a hard time spinning around the wheel, it's free to rotate. It's greased, right? But it still is providing a normal force, upward force. Well, let me ask you this. Can we rule out whether there's any horizontal force from that based on all the forces in the problem? And after all, here's my free body diagram, right? I've got a downward force of gravity. I've got a force due to tension that's down over here, right? And now I've got a force from the hinge. Can it possibly have a horizontal component? Well, in principle it could, but if it did, what would happen? It would have to be accelerating in the horizontal direction. In this problem, it's nailed. The center of mass is not moving throughout the entire problem. So there's no acceleration of this object. So then is it possible then that there's a horizontal component to the force from the nail? It can't have a horizontal component. It must only have a vertical component. Force nail, right? In fact, if I'm going to draw the scale, I better make it really big, right? Because it has to be that plus that for that thing not to be accelerating. Does that make sense? For F medical AMA. I think it's fine if on the test you draw a horizontal piece and a vertical piece, you won't be penalized for that at the level of the free body diagram. But you better figure out pretty quick in the problem that the horizontal part's 0, right? Otherwise you're going to have crazy answers. So yeah, that's a good question. The way I would handle it, if you draw your initial free body diagram, as we were saying, suppose you decide to make the force drawing to the right in this friction problem. You don't know which way's going to point in the beginning. Maybe you've got so much stuff going on, there's no way you can tell. That could happen, right? Or even if you do have enough stuff, like in that case, whatever. But let's say you do that, and now you turn through it, at the end you get a negative sign, and you say, oh, I see. Clearly the force is pointing the opposite direction as I drew it. You just say so. You don't have to go back and change your drawing. You might choose to, but the problem with going back and changing your drawing is you better change your equations to agree with the drawing, right? Like, graders are looking for self-consistency in your answers. They're using every cue they can to figure out whether you're on the ball or not. And so what you don't want to do is have conflicting information on the page. So I wouldn't go back and change things piecemeal. The way I would handle it is I would go work the problem at the end and say, oh, I got a minus sign for what I was calling the magnitude of the force of friction. Therefore, the force of friction is actually pointing to the left, not the right, as I drew it. And just say that, and then, right? And so I think that solves the problem. And then it's clear how your thought process, and you're less likely to have some inconsistencies that are left behind. Of course, if you can, try to intuit which way it's going to go in the beginning, and then it just makes your life easier when you're going through the exam. Yeah. Tortoise on a lever. Yeah, you bet. Yeah. Okay. So here's the thing. There's no fluids tonight on tonight's exam. The problem you're asking about has the free body diagram for what, the lever? So if you've got a lever like this and there's a hinge right here. Oh, to the end? Oh, I forget. All right. And there's a plunger here and some piston. And there's a tortoise. Oh, all right. All right. So what's the free body diagram? How many forces are in this problem? This thing has some mass. So it's probably got a gravity acting. Where's the gravity acting? Center mass. So I would say, okay, center mass, I got my mg. I've got my, and also downward force to the turtle, right? That's mass of turtle times g. This is mass of lever times g. Or I could also put f sub turtle and s. It doesn't matter how you want to label it as long as it's clear what you mean, right? This is a little more informative because it tells me how to put, I can sort of skip a step in my algebra and go right to the, and then, so what about this plunger? It depends on the problem. The force here could be up or down. If what's going on is that this guy is pushing down and then this is holding it up, well, which way is the force pointing? Better be up. Oh, I see. You're saying how do you know what the direction of it is if it has a horizontal? Yeah, that's a good question. I think I would assume up here. I forget the way I phrased the problem or what I told you, but I think this is probably what's intended. I don't remember this. Oh, you guys are reading all that good. Go through all those problems. So I think it's probably intended to be an upward force. In fact, if you didn't know, if it had a horizontal component potentially, which it could, in principle, the problem is you could have forces that are opposing each other in here, and you can make them as big as you want and still satisfy F at n equals ma given what you're given. So what I should have done if I didn't was have this thing, was make some statement like there's a plunger right here, and this is free to rotate, so that the force has to be, like if this is free to rotate right here, if there's a hinge here, then, and this thing could rotate down here, so it could, that would guarantee that the force has to be along the direction. I think that's true. I have to think about that actually. Think about that's true. So I don't remember how I phrased it, and I have to go through it to remind myself, but I think if I were solving this problem, what I would do is say, well, I'm assuming that the force here is vertical. The hinge force can certainly have a horizontal or vertical force, component to its force, right? So I would draw it as two separate forces explicitly. F hinge x, F hinge y. You can also, if you prefer, I don't prefer to do it, then by that I better have my y and x axis agree with that. So here's the thing. I would choose this thing to point, if I don't know which way it's going to be, left or right, this force, although given the rest of this. Well, so to figure out the direction, so I don't have to look at the problem to see. It depends on what you're asked and how it's, no, excuse me, it depends on exactly how it's set up. If the problem could be set up with two hinges here that could both have forces in horizontal and vertical directions. If that's true, then my Newton's second law in the x direction, they have to have equal and opposite horizontal components because they're the only non-vertical forces in the problem. If you know one of these only has a vertical component, for whatever reason they give us in the problem description, then you know the other one must as well. Because, so in other words, if this is the only potentially horizontal force in the problem, just like over here, if the hinge force here, the nail force is the only potentially horizontal force, then it's going to be zero because if the object is not accelerating. And if this problem is a static problem, this thing's not moving, and I know the other force, so this must be zero. Now, if both these can have horizontal forces, then we don't know unless there's some other information that's given. It could be in many forms, right? It could be, you could be told to assume that this is only vertical, or it could be that, I have to go back and look at it to see exactly how it was in that problem. But you'd have to have some other information. The thing is, solving this problem, the thing about static problems is you've got three different equations, right? In general, in this class, because we have two-dimensional set like this. You have x component of Newton's second law, you got y component of Newton's second law, and you've got what? Yeah, the Newton's second law for rotations, right? The net torque equals I times alpha. So in this problem, and in all these problems, once we just, if you want, we don't have to, it's really easy to see what's going on. Like if this is an accurate drawing of the situation where this only has vertical, we don't have to invoke the vertical Newton's law, Newton's second law. We don't have to invoke the rotary version of Newton's second law. We can just look at the horizontal and tell that has to be zero. So that's really nice. It isn't always that way. It'll sometimes be you'll have to combine several things to figure it out. But if you're clever about it, you can usually figure out what the answer is just based on one of those three things. And of course, when I say Newton's second law for rotations, you have lots of choices about where you choose your pivot point. So for a static problem, anywhere. So anyway, so in general, be clever about which thinking about if one of those laws can get you pretty far. But some problems probably require you to use two or three of them to get it all the way solved. And one trick on all these sort of exams is to figure out what's easy and what you can just jump to the answer with a simple thing, and when you really need to invoke two different rules. Yeah. Should I do a demo? You guys are dying. Should I break a glass? Let's break a glass. Yeah. So this is going to be about resonance. I'm not going to test you on damped or driven harmonic oscillators. But I'll just tell you what it means. If you have a harmonic oscillator, it must oscillate at some frequency. We calculated what the frequency was last time, right? It's for a mass on a spring. It's square root of, what is it? Omega is square root of, let's see, is it bigger with mass or smaller with mass? Smaller. You guys, you want to demo, don't ask me questions. Mass goes to the bottom, top is spring constant. So this is the frequency it wants to be driven at. That's the natural frequency of a harmonic oscillator. Most harmonic oscillators are imperfect. They got friction or some kind of viscosity or something like that. And if you go through the math, which we won't do, the book does it, and you may have a homework problem or two on it, but it's not going to be on an exam. There's a damping term that says, it's like a friction term, kind of opposes the motion, except that it's proportional to velocity. Unlike friction we've seen, which isn't proportional to velocity. Let's see if I do this right. Oh yeah, so what have I got here? Can I get, I'll turn this on. And you have to turn the lights off and turn on a strobe light. See if this works. Give me a second so I can figure this out. Oh, there it is. So right now I've got a strobe light on this thing, and there's a camera right here. Is this camera turned on? These are my bifocal light. Where's my camera? Don't get old. It's my advice to you. Oh, can't figure this out. So I don't know if this is on or not. Let's see. Power. Let's try power. No. Doesn't like power. Let's try this. Oop. Oh, no luck. I don't think it's turned on. Well, I'm hoping you'll be able to see this, but you may not. Through this thing. Oh. Oh man, too bad. I thought it was already turned on at the beginning of class. It's possible that it shut down. No, it's on though. I think it is on. Oh, I just need to turn it off and turn it back on again. All right, let's see if that does it. Oh, there it is. All right, so what am I doing? I'm using a strobe light to look. I'm going to put my safety goggles back on. I got the strobe light on this glass. This annoying sound you're hearing is coming from a speaker that's right up against the glass. Because of budget cuts, we no longer do this with a Ming vase. We use a beaker, and the beaker is sitting here. And when I turn up the amplitude of the sound, I'm driving this thing at its resonant frequency. I'm at resonance. So I'm trying to drive it so hard that, and what you'll hopefully see when I turn up the sound, it's really annoying, but what you'll hopefully see is deformations in the shape of the glass. So when you have these old, is it real, is it Memorex? It's way before you guys were even born, these commercials on TV, but they would play a tape and some opera singer would, right, and she'd break the glass. And because she's singing at the resonant frequency, at the omega naught, the omega naught of the glass in question, and it would shatter the glass. So let's see if it works. I'm just going to keep turning it up, and you'll start seeing it deform, and then I'll be showered in shards of glass. See? Is it working? Oh, I need gain over here. This is the powerful part here. Oh yeah, it's starting to wiggle. So I'm going to keep going until it breaks, all right? Yeah, that's a real deal. It works. Yay. So that's an example. Yay, isn't that fun? What fun. So the goal there is to point out resonance. If you drive something away from resonance, what happens? Suppose in the old gangster movies, the bad guy would come in and grab somebody and shake him. He'd shake him way faster than resonance. And so what happened? The guy's head was always out of phase, right? I'm showing you in slow-mo, right? So he pushes, his head is always 180 degrees, or pi, out of phase with the driving force, with the driving frequency. So he's doing this, and the guy's head's flopping, right? Out of phase. Now if you push him really slowly, right? Now his head stays with his body. So his head is like an oscillator, right? It has a resonant frequency based on the spring of his neck and the mass of his head. And that thing goes back and forth. It wants to go back and forth at some frequency that's about like this, right? If you do it too fast, you're out of phase. You do it really slowly, and then it tends to move with you, right? If you're trying to, and, my daughter's on the swing, okay, so that's an example of a harmonic oscillator, essentially, right? It's a pendulum you saw to a good approximation, small angle approximations, like a harmonic oscillator. If I push her on the swing, so there's a couple things. One is people usually stand way back so they get knocked over when they're doing the swing. But where's the point in the swing where I would get the most work for a fixed amount of force, acting over a fixed amount of time? Where should I push? So if she's going back and forth, should I be right in the middle or should I be way at the end? Actually in the middle for a fixed amount of time, right? Because as she comes through, if I push with some force of whatever it is, 20 newtons, I exert some force. If I exert it over a larger distance, I get more work out, right? Work is force times distance. It doesn't matter how fast you're moving during that time, it matters how with the forces and with the distances. So I get more work in the middle. Well, another thing, so that means if I push for a fixed amount of time for a fixed force, I get more work out if I do it in the middle. So that's where I stand. I'm the only guy, everyone else is standing way in the back pushing her kids. I'm in the middle pushing, and she goes really high, fast. She's right, she loves the swing. I would be sick if I run the swing as much as she is. So that's one thing I was going to mention. Another thing is in terms of driving. When I push, the driving frequency I use is the one that's matched. I'm pushing her at resonance. I'm giving her, so the forcing I'm doing is in keeping with the frequency of her oscillation. In other words, I stay in phase with, and actually 90 degrees out of phase, but I'm at the same point of the cycle every time pushing her. So that I'm always pushing her when she's going that way, and I'm pushing her with a force that goes that way. What we did right there is we're forcing the glass in resonance, right, with the omega naught of that glass. The glass, if we did a bunch of math, we could figure out what the effect with the mass and the kr for that spring on mass system, and we're forcing it at a frequency that agrees with the frequency it wants to be, that is most effective for putting energy into the system. You put so much energy in the system, we blew it apart. That's how much energy we put in. If you drive it off of resonance, then she doesn't get very high in the swing, and we don't blow the thing apart. Anyway, so that's enough on resonance. We'll do waves next week. We got a midterm tonight, so I'll see you guys.